Hi and welcome. It's Saturday Extra and it's time for Physical Sciences now. My name is Tinyiko Kosa, and if you were not aware, this is lesson number 20, and today we're going to talk about organic reactions. Now, under organic reactions, these are the type of reactions we'll be talking about. We'll be talking about substitution reactions, we'll be talking about combustion, which is oxidation reactions. We will be talking about elimination reactions. We'll be talking about hydrogenation. We will be talking about halogenation. So there's so much of genations here. We will also have hydrohalogenation. And you can see that this one is actually a combination of that and that. Now we will also have something called hydration. We'll also talk about esterification. Right. Now, this type of reactions, you need to master them, you need to understand them, because they are going to help you to answer most of the questions in the exam. And you know that there's quite a lot of marks carried in this section of work. So it is actually an easy section where you can tell yourself, I'm going to score more marks on this one. And you study it and you perfect yourself on it so that when the exam comes, you're ready for it. Now, let's start with the first type of reaction. We're going to talk about substitution now. Now, this is a reaction in which an atom or group of atoms in a compound are replaced. You see, substitution, you are replacing something. Now, if you are substituting a player in a game of soccer or rugby, you are actually taking that player out and putting another one in his place or in her place. So what is happening, you are substituting, you are replacing one by another. That is the meaning of substitution. So substitution reaction does exactly that. We are replacing some atoms or some group of atoms by another. Okay, so that's substitution. And this happens when we talk of alkanes in organic chemistry. Why alkanes? Because alkanes are saturated. We say that alkane molecules are saturated. What do we mean by them being saturated? They've got everything that they should be having in terms of the atoms that are there. So if you are to change them into something else, you need to replace what is currently available. So that is what is meant by saturation there. So alkanes are saturated, so they undergo substitution reactions, and since they cannot, we don't have anything to prolong them, to get them into something else. If we want to change them into something in their current state, we need to replace what is available. Now let's quickly look at this example here that will show us what we mean by substitution. Show how chloromethane, dichloromethane, trichloromethane, and tetrachloromethane are formed through substitution reactions between methane and chlorine. Okay? Now, firstly, we're talking about chloromethane. How is it formed? Okay, now what we know is that methane, it's a CH4 organic molecule, the simplest alkane we can talk about. Now, if we want to make it chloromethane, it would mean that one of the hydrogen atoms have to be replaced by chlorine. So we will add here in its place chlorine. We know that chlorine is Cl2, but allow me to write it here in terms of the bonds between them. It's a diatomic molecule, and that is how it should be. Now, when this reaction takes place, this is what is going to be formed. One of the hydrogen atom will be replaced by the chlorine atom. So what is going to happen is that you have this at the end. So there's the hydrogen, hydrogen, hydrogen. But this hydrogen here will be replaced by a chlorine atom. Then the question is, if this hydrogen atom has been replaced by a chlorine atom, where does it go? Where is it going to go to? And where will we find it after this? Because we can't lose it. Matter is never lost. So what is going to happen is that this H here, this hydrogen atom, with this other chlorine atom are going to react together to give us what we call hydrochloric acid, HCl. Now, this molecule here, if you like, you can write the molecular structure for it, or molecular formula. That will be CH3Cl. Now, this is chloromethane. Okay, so that is how chloromethane is formed by substitution there. So that was the first one. The second one we have to talk about is dichloromethane. Now, if we're moving to dichloromethane, we should be moving from chloromethane. So we are from there, chloromethane. You can see it is chloromethane because of that Cl over there. Now, if we add another Cl2, remember here I explained how that Cl is the bond between the Cl atoms are, so that you've got a diatomic molecule Cl2. But this time, because now you understand that, allow me to write it in its original form, Cl2. Now here, what is going to happen? Exactly what happened earlier on is going to occur, where one of the hydrogen atoms is going to be replaced by a chlorine atom. So say it was this hydrogen atom. So we'll have chlorine there, hydrogen, hydrogen. Plus, where does the other chlorine atom go? And the hydrogen that we have replaced, this hydrogen here. Those two are again going to react together to give you your hydrochloric acid. And now you have got your dichloromethane. So this is dichloromethane. Okay, let's move on. The third one, we need to show how trichloromethane is formed. To go there, we start from dichloromethane. So we're starting from this one. Starting from this one here, dichloromethane. We're adding chlorine to it. By now, you should be quickly able to show what is going to happen. Obviously, one of the hydrogen atoms, let's say that one, is going to be replaced by the chlorine atom. Okay, we still have hydrogen down here. We have got chlorine there. Plus, this hydrogen here that has been replaced now, plus the other chlorine atom, they combine together. They give you your hydrogen chloride gas or hydrochloric acid. And this is your tri. Now, tri for 3. Trichloromethane. Okay, so that's how trichloromethane is formed. Going down to tetrachloromethane, that means you've got a methane with 4 chlorine atoms on it. Now, how does that happen? We're going to start from trichloromethane. So here is our trichloromethane. Trichloromethane. It only has 1 hydrogen atom. Now, if we add chlorine to it, you can actually tell what is going to happen. The very last hydrogen atom is going to be substituted by a chlorine atom. So what are we going to have at the end? We're going to have this. We're going to have the carbon atom surrounded, completely surrounded by chlorine atoms, and that hydrogen atom attaches itself to the other chlorine atom to give you your hydrogen chloride. So this is your tetra for 4, tetrachloromethane. Okay, now I think this helps us to understand clearly what substitution reaction is all about. So you are replacing something by another. That is substitution in short. Right, let's move on. Let's now talk about hydrolysis. What is hydrolysis? Hydrolysis is a type of substitution reaction where haloalkanes react with water to form alcohols. So you've got hydrolysis as a form of substitution. Okay, hydrolysis. Now, why does it have to be called with a separate term or a completely different term, yet it is substitution? It is because, or especially because, this reaction occurs with water. We have got haloalkanes reacting with water, hydro for water. So we are hydrolyzing these haloalkanes. Now, we can ask ourselves, what are haloalkanes? We can go back to example 1. All these, the chloromethane, dichloromethane, trichloromethane, tetrachloromethane, these are haloalkanes. Why haloalkanes? The word halo, let me just use this space here. The word halo comes from the word halogens. And what are halogens? These are group 7 elements. Okay? These are group 7 elements. And what are those? We've got chlorine, we've got iodine, we've got bromine, we've got fluorine. Okay? This diatomic molecules of the halogens. So we're talking halo something because those molecules contain the element or atoms of halogen elements. So here, hydrolysis refers to the reaction between haloalkanes with water to form alcohols. How is this done, or how does it happen? Make use of structural formulae to show the reaction between bromomethane and water. Now, bromomethane would be a haloalkane. Why haloalkane? Because it has got this bromo component from bromine. Bromine is an element from the halogen group. Okay, it's one of the halogens. So let's use structural formula to show the reaction between bromomethane and water. Let's write it down. What will be the structure of bromomethane? Methane, 1 carbon atom. Bromomethane would mean one of the hydrogen atoms is substituted by or replaced by bromine. So that will be the structural formula. They say here it is reacting with water. Water is H. Allow me to do it this way now to show the bonds between the oxygen and the hydrogen in the water molecule. What is going to be formed? Okay? Now, we are told that when hydrolysis takes place, an alcohol is formed. Okay? One of the products formed is an alcohol. Now, definitely it tells us that one of the OH here is going to come to the methane here. How is that going to happen to give us the alcohol? In this case, if this is bromomethane, the alcohol we're looking for should be methanol. Okay, so this sort of guides you as well as to what is going to be formed. So what we are going to have here is that we're going to have C, H there, H there, another H there, but the bromo part, which is the bromine atom section, is going to be replaced. That's why we say it is also a form of some It's also a form of some, excuse me, that's your other hydrogen atom. So the Br is going to be replaced by the O-H bond to make it an alcohol. Plus, now what has happened here? You would say that when this OH has now come there, all right, what is left here is this H. Definitely the H and the Br atom are going to meet to give us hydrogen bromide. So that is a hydrolysis reaction. You are having a haloalkane reacting with water to give you alcohol and a hydrogen halide. Hydrogen halide, I'm giving it in the general because this halide part here could be chlorine, chloride, could be iodine, so it could be iodide, okay? Iodide in this case. In this case, it will be chloride. If this was chloromethane, this was going to be hydrogen chloride. If this was iodomethane, this was going to be hydrogen iodide, okay, in that way. So that is hydrolysis. Reaction between a haloalkane with water to give you the ethanol of that alkane plus a hydrogen halide. Okay. Next, let's talk about addition reactions. Now, this term here speaks for itself. Okay? That term there speaks for itself. You are adding something. You are not substituting. Whatever is there remains there, but you're bringing more into the molecule. All right? Now, earlier on I said with alkanes, we're talking about saturated molecules. They have got all of what they need. So you can't add anything into them. The only thing you can do to them is to substitute what is there with something else. But in this case, where we're talking addition reactions, it means these molecules are unsaturated, so they don't have enough of everything they should be having, so we can add more to them. And what are those molecules that, or what are those organic molecules that are not saturated? These organic molecules that are not saturated are what we call the alkenes and the alkynes. These are unsaturated hydrocarbons. And because they are unsaturated, they are reactive. They can take more. They can still receive more in their molecular structures. So this addition reaction is a reaction whereby the reacting substances form a product whose molecular mass is given by the sum of the molecular masses of the reacting substances. So whatever is going to be formed, its mass, you're going to get it by adding everything that you put together. You are not replacing anything, you are just adding, and then the masses obviously are going to be added on to give you the mass of the product that is going to be formed. Right, let's have a look at how this reaction happens. But just before that, be reminded that when we talk alkenes, we're talking about hydrocarbons with double bonds between carbon atoms. In other words, you've got that situation there. When we talk alkynes, we're talking about hydrocarbons with triple bonds between carbon atoms. So you're talking about that, okay? Triple bonds between carbon atoms. Right. Let's move on. Let's come to example 3. Make use of structural formulae to show the reaction between ethene and chlorine. Now here we've got ethene, not ethane. Now ethene would mean I've got a double bond between carbon atoms. It's ethene, and therefore it's an alkene. It will be having hydrogen atoms attached to carbon atoms in that way. It is reacting with chlorine. So remember chlorine, Okay, allow me to write it like this again this time. What is going to be formed here? Now, listen carefully here. We've got a double bonds between carbon atoms. What is going to happen is that one of those bonds is going to break. And when it breaks, each carbon atom would have at least one more bond to form with any other substance that can come its way. So when this bond here, for example, breaks, so it breaks up, what you're going to have here is a C with now a single bond between these carbon atoms, just a single bond between them. The broken bond, which was the top bond, will be like that. And what happens, you've got your H there that you started with. You also have your H there and your H there that you started with. But then this broken bond here has created two spaces in which any other atom can come in. And now, what is that atom that can come in this reaction? Obviously, these are atoms of chlorine because ethane here is reacting with chlorine. So you're going to have one of the chlorines going there. And you will have the other chlorine atom, which is this one, going there. So you have got your chloromethane formed. So you will see that you are moving from an alkene, you make it react with chlorine, you're moving from ethene, reacting with chlorine, you come to dichloroethene. So you're starting with ethene. Let me write it down here. React with chlorine, you form dichloroethane. It has to be ethane here because it's a single bond there between carbon atoms. Now, that is how the reaction takes place. Let's look at the next one here. The reaction between propyne and bromine. Now, what homologous series does propyne belong to? It belongs to alkynes. And this suggests that we have got triple bond between two of the carbon atoms. So that will be propyne. Because here we already have 3 bonds, it means I only have one hydrogen attached to that carbon. The same thing will apply here. You've got 1, 2, 3, 4 bonds, and therefore no hydrogen atom can be attached to the middle carbon atom because it has all her bonds used up. The last one can take 3 more. So that is propyne. Now, when it reacts with bromine, so this will be plus Br2. If it reacts with bromine, what is going to happen? The same thing is going to happen. One of the bonds here is going to crack. Okay? The top, say it is the top one that cracks, that breaks up. What you're going to have is this. You're going to have double bond there. So if that is a double bond, it means you would have one hydrogen there, and definitely you would have one of the spaces taken up by bromine. Then the next bromine atom would come here. Remember, this one has also created a space there. So bromine there, plus your last carbon atom. Okay? Now, let's check what has happened here. You started from an alkyne triple bonds. You are ending up with double bonds between carbon atoms. And what are these now? These are halogens, bromo. So this is a bromo molecule. It is a dibromo because we have got 2 of these bromine atoms on it. But dibromo what? We remember the naming that we spoke about. from the side where the radical is, we start counting or numbering our carbon atoms. This is 1, 2, 3. I can't start from right to left because the bromine, the halide part is closest when I start from the left. So I would say this is 1, 2, dibromo what? Propene. And I can even continue actually to tell you what happens here with where the triple bond is, because that is not enough in terms of the IUPAC way of naming. I also need to show where the double bond is. So I can write that in full as 1, 2, dibromo prop. Where is the double bond? On carbon number 1. So prop 1 in. And that becomes a full name for the molecule that has been formed, okay, in this reaction here. Okay, now let's move on. Let's now talk about hydrogenation. We were talking about, remember, we were talking about addition reactions. Okay, we have added there. And now we're talking hydrogenation. Okay? Now, hydrogenation is also some kind of addition reaction, but it is special in its way. That's why we call it the way we do. Why? Because in that addition, all we are adding is hydrogen. Okay, so we're adding hydrogen atoms to unsaturated hydrocarbons. And what are those unsaturated hydrocarbons? We know unsaturated hydrocarbons are the alkenes and the alkynes. All right, those are the ones that are unsaturated. Now let's look at this example here to show what happens here. Show how the following molecules can be formed through hydrogenation. Okay, propane. This is a good question. Propane, how is it formed through hydrogenation? Now, for us to move or to produce propane from an unsaturated hydrocarbon, that unsaturated hydrocarbon has to be an alkene. It can't be an alkyne. In other words, it has to be one with double bonds between carbon atoms, just a double bond. So that when we break that bond, we go back to an ethane or propane or methane. To an ethane, propane, or butane. We can't talk ethane. Why? Because, we can't talk methane. Why? Because methane is the simplest one with one carbon atom, and therefore we can't be talking about double bonds between carbon atoms. So, if we are moving from something to propane, that something has to be an alkene, so it means we're moving from a propene, okay, to propane. Now, this is done by the addition of hydrogen, what we call hydrogenation. So let me just work out how it's going to be here. So I've got a propene molecule here. All right. Here I would have H. I would have one H there. I would have 3 there. This is a propene molecule. Now, if I add hydrogen here, hydrogen, remember, is H2, just like I did with chlorine. Allow me for now to say H-H to show that there is a bond between the hydrogen atoms to give us the hydrogen gas. What happens here? The same thing. One of the bonds cracks. It breaks up, And what happens when it breaks up? You now have a single bond between carbon atoms, and each of the carbon atoms where the double bond was has got one space for more other things to be put in there. So what we have here is that you still have your hydrogen, the first one, this one, and you have got your second one there. But then on this one, remember you only had one hydrogen, and then the last one you had your 3 hydrogens. The 2 hydrogen atoms here then attaches themselves on the available spaces on the propane molecule. Now this is the propane. This is how the propane is formed, okay, through hydrogenation. Hydrogenation of what? Hydrogenation of propene will give us a propane molecule. Now I can also see that if I talk hydrogenation of propyne molecule, it means I will come down to propene molecule. So you move one step down in the homologous series. All right, let's move on. Let's show how ethene is formed through hydrogenation. Now, ethene has got a double bond between carbon atom. If I am to come down to ethene, I must be from ethyne. So what I have initially is this, is a triple bond between carbon atoms, and therefore this will be very incorrect. So it's a triple bond between carbon atoms, therefore I only have one hydrogen atom attached to each of the carbon atoms. That's what the ethene molecule would look like. If I then bring in the hydrogen gas, hydrogen molecule, what we're talking about will happen. One of the bonds is going to break up, so what I'm left with is a double bond there. So what happened? There are spaces now for that, okay? And then here, what do I have? I've got that single bond there, so one of the bond will be there, and I will now be having 4 on the other side as well. So let me just write this nicely like that, okay? So there is the first hydrogen for this carbon atom. There is the first one for the second carbon atom. Each of these hydrogen atoms are going to find spaces at each of the carbon atoms, and that is what we have. And what is this? This is an ethene molecule. So from an ethine molecule, if I add hydrogen, which is called hydrogenation, the process is called hydrogenation, I end up with ethene, which is an alkane. So that is what happens. Now let's look at this one. How do I form an ethane molecule? Okay, through hydrogenation. This should be simple now to understand. Remember, you move one step down. If what is formed is ethane, I must be coming from ethene, all right? And what is ethene? There is ethene. Okay, there is an ethene molecule. You are hydrogenating it, so you are putting hydrogen atoms onto it. H2. Okay, this is H2. All right, I'm writing it like that so that we understand what's happening in terms of the bond formation. Right, so one bond breaks. I've got now single bonds between carbon atoms. There is the first hydrogen, the second one that I had on that carbon atom, the first one and the second one that I had on this carbon atom. These two spaces are now available. Each of the carbon of the hydrogen atoms are going to find themselves spaces in each of the 2 carbon atoms in that way. And what is formed here now is my ethane. So that's an ethane molecule. Right. Let's look at halogenation. Now, halogenation, just like hydrogenation. We spoke of hydrogenation earlier on. It is the addition of hydrogen. Now, what would you then make of halogenation? It will be an addition of a halo molecule, a halogen, chlorine, iodine, bromine, etc. Now, let's look at it. Halogenation is a reaction whereby a halogen is added to an unsaturated hydrocarbon. Again, we are adding onto unsaturated unsaturated organic molecules. You cannot add to a saturated one. You can only replace, you can only substitute on a saturated one. If you are to add, it has to be on unsaturated hydrocarbons. Okay, so those will be the alkenes and alkynes. Let's look at example 5. Show how the following molecules can be formed through halogenation. Now, the first molecule we are to look at is 1.2 dibromoethane. Now, in the same way, if this is an ethane molecule, it means that I am from ethene, all right? So it would mean that I've got this situation at first. I've got a double bond between carbon atoms for it to be an ethene. That's what I have. Now, if I add a bromine molecule, Br2, what am I going to have at the end? I would have one of the bonds breaking up, so the same thing that we are looking at there. So one of the bonds breaks up, so I have a single bond between carbon atoms now. So what is remaining here now? There are, for each carbon of the carbon atoms, there are those 2 bonds that are now available. The other 2 are still occupied by my hydrogen atoms, like that. So these ones that resulted from the breaking up of the double bond between the carbon atoms, they are now available to take up the bromine atoms. And that is my 1.2 dibromoethane molecule. Right. Moving on, we're looking at this one here. 1.2 dibromoethene. Now, if I am coming down to ethene, I must be from ethyne. So that would mean I would have one molecule of ethyne having triple bonds between carbon atoms, and that is what I initially had. Now, if I introduce bromine here, Br2, what is going to happen? One of the bonds breaks up. So what I have now is a double bond between carbon atoms. One of the hydrogen atom that was already there is still there on this carbon atom. The same thing there, still there on that carbon atom. But then from the broken bond, we have got 2 available spaces on each of, one on each of the carbon atoms. And therefore, the bromine atom can come in there, and the other one can also come in there. So I've got my 1.2 dibromoethene molecule formed. Lastly, 1.1 0.2.2 tetrabromoethane. Now, what is going to happen here? Okay, what is going to happen here? Tetrabromoethane, where will it be coming from? Okay, it surely should be coming from a dibromoethene. So dibromoethene would be this, what we had earlier on. So there is the Br, there is the Br, and there is the H, there is the H. Now, if I bring in Br2 molecule here, what is going to happen? The same thing, one of the bonds is going to break. So you have now that. Remember here you had a Br and H. You had H here, you had Br there. So each of these Br atoms are going to attach themselves there. So one of the bromine atoms there and the other one at that point. So what do you have here now? You've got exactly that. On carbon atom number 1, you've got 2 bromine atoms, so 1.1. On carbon atom number 2, you have again 2 bromine atoms, 2.2. Tetrabromoethane. Tetra because you've got 1, 2, 3, 4 of the bromine atoms around that alkane molecule. So you've got a 1.1, 2.2 tetrabromoethane formed in that way. Okay, hope that makes it more understandable, the halogenation. Let's move on now. Let's talk about hydration. What is hydration? Now, hydration has got something to do with water. This is the addition of water to unsaturated hydrocarbons to produce an alcohol. So you've got an addition of water to an unsaturated hydrocarbon. In the process, you are forming alcohol. How does that happen? Now, it has to be an unsaturated hydrocarbon. Okay? So again, we're talking alkenes, we're talking alkynes, because these are the ones that are unsaturated. So we can't be talking alkanes here. All right. Let's look at example 6 now and see how hydration takes place. Show how water and ethene combine in the presence of a catalyst, which could be platinum, to produce ethanol. Okay? So the alcohol that is going to be formed is ethanol. Why ethanol? Because we are from ethene as our unsaturated hydrocarbon. Now, what is ethene? Ethene has 2 carbon atoms, a double bond between them, and you've got then your hydrogen atoms like that. Hydration, addition of a water molecule. So allow me to show the water molecule bonds in that way. The H2O, that's your H2O. Now, what is going to happen here? The same thing that we looked at earlier on happens. That bond breaks up. So you've got a single bond there. You still have, so that those 2 spaces are now available. You still have your hydrogen there. You still have your other hydrogen here. You still have your hydrogen there and your other one there on that carbon atom. These two spaces are available now. What is going to happen with them? One part of the water molecule, which will be the H, the hydrogen atom there, would come, bond itself onto the carbon atom there. This one would go as a group to bond there as the OH. And what do we know about the OH? That is your alcohol. This is ethanol. Okay? The alcohol, what gives it the alcohol nature? The OH group makes it an alcohol. So that is how your methanol is being formed. The addition of water to an unsaturated hydrocarbon. Okay? And we call that type of reaction hydration. Right. Now let's come to hydrohalogenation. Now this word here can be broken up into three parts. Hydrohalogenation. Now, genation, what am I drawing? Am I writing here? It should be genation here. Now, if you check here, you have combined two things. You have combined hydrogenation and halogenation, and you have hydrohalogenation. In other words, it means you are having the two processes happening at the same time. You are bringing in a hydrogen, you are also bringing in a halogen in that process. So that is hydrohalogenation. Now, let's look at an example. But then we need not to lose focus of the fact that we're talking about unsaturated hydrocarbons. So when we're talking about these reactions, we're saying this is a reaction between a hydrogen halide and an unsaturated hydrocarbon. Now, what are hydrogen halides? Okay, what are hydrogen halides? Hydrogen halides are substances like the following. Let me start with the one that you are so familiar with. You should be working with this one a lot. It's an acid, hydrochloric acid, HCl. It's a hydrogen chloride, so it's a hydrogen halide. We can have hydrogen bromide, hydrogen iodide, hydrogen fluoride. All these are hydrogen halides. Okay, so this is what we mean by hydrogen halides. Right, now let's quickly have a look at an example to see how hydrohalogenation takes place. Make use of structural formulae to show the reaction between ethene and hydrogen iodide. Now, ethene is an unsaturated hydrocarbon, and it's an alkene, so it has got double bonds between carbon atoms. So that will be its structural formula. Okay, that will be ethene. It is reacting with hydrogen iodide, so hydrogen iodide is Hi. Allow me to put a small line there to say that's a bond. Then, when this reaction takes place, this bond is going to break. This one is also going to break. Now, what happens after that? What you have is that you now have a single bond between the carbon atoms. One more bond is available there, and one more bond is available there. These ones are still there. So you still have your H, your H, your H, your H there, your hydrogen atoms. Now, these two spaces that have suddenly become available, one of the space will take up the hydrogen atom, and the other space is going to take up the iodide or the iodine atom. So what do you have here? you have got an hydroethane. So that's what you have here. Hydroethane. That's an example of hydrohalogenation. You are bringing in a hydrogen and you are bringing in a halogen. So it's a hydrogen atom that is coming in. It is also an iodine atom that is coming in. So you are bringing in a hydro part and an iodo part, the halide part, iodo part there. This is what you are bringing in, hydroethane. Let's now look at elimination reaction. Now, elimination. When you eliminate something, you get rid of that thing. Okay, you get rid of this thing. You remove it. So this type of reaction is a removal of atoms or groups of atoms from large molecules. So you are removing what was there already. And you're not replacing it with any other thing, you're just removing it. Okay, so when you remove it, you're going to end up with something else and you're going to have other things taken out. That is removal. So we call this type of reactions elimination reactions. Okay, and we've got two types that we can look at when we talk elimination reactions here. We have the dehydrohalogenation. Now, the word D means you're getting rid of something. Dehydrohalogenation, it means you are getting rid of a hydrogen, you're getting rid of a halogen, hydrogen and halogen here. So here you're getting rid of a hydrogen, you're getting rid of a halogen. Hence the word dehydrohalogenation. Okay? Lastly, dehydration of alcohols. Now, remember hydrolysis, or the word hydration, has something to do with water, addition of water or putting of water into some substances. That's hydration. Now, if you are dehydrating something, it means you are getting rid of water. So you are actually here removing water. So dehydration of alcohols will mean that you are removing water from alcohols. Okay. Now, let's look at an example here and see how these processes take place. Example 9. Show how the formation of ethene through the action of potassium hydroxide on bromoethane. Okay? Now, what do we have here? Bromoethane is a haloalkane. Okay? Now, you are making this haloalkane to react with potassium hydroxide. And at the end, we are forming ethene. Now, let's quickly see what happens here. So you start with bromoethane, okay? And at the end, you are forming ethene. So what we have, let me start with the product here. I've got here ethene being formed. Okay? Something else is also going to be formed. Okay? And what is that something else? If this reaction is a reaction between potassium hydroxide and bromoethane, and then I end up with ethene. So it means that I am going to have something like potassium bromide formed, and I'm also going to have something like water also being formed. Okay, so this is what I'm going to see happening. Why am I writing it like this? I know that, okay, well, this is given to me is the ethene molecule that is going to be formed, but there is the potassium here. It's going to likely take up the bromide, the halide there, to form the potassium bromide. And what I also know is that I've got an alcohol, potassium hydroxide, KOH. Definitely that OH there, if it comes together with hydrogen, it's going to give me a water molecule. All right? Now, this side, what would I have started with if I've got that? I must have started with something like so that's ethene. I would have started with bromoethane. So I've got that. This now reacts with KOH. Let me put that small bond there to show that this is happening. Now, what is going to happen here, I see that this one come together, they form the potassium bromide. Okay? What am I left with here? I'm left with the OH. This is the OH. Now, that OH there cannot be remaining alone as a product there. Obviously, one of the hydrogens, maybe that one, will come in to form the HOH bond there, which is the water molecule. Now, if I have removed that H and that Br, which is dihalo, okay, and these two bonds are now available. So what happens is that the two bonds come together down onto the carbon, between the carbon atoms, give me the double bond there. So I now have an ethene molecule. So that is actually what is happening there. There has been a removal of hydrogen and a removal of bromine atoms there. And that is dehydrohalogenation. You are removing the hydrogen and the bromine there. Right, let's now talk about the dehydration of ethanol. Ethanol is an alcohol, so we are removing the water content from ethanol. Now, what is ethanol? We have got C to C, then to OH. That's ethanol. Okay? And there are our hydrogen atoms. Now, dehydration. Now, dehydration, like I said, the removal of water. Now, in chemistry, one very important substance that we know to be having a dehydrating action is what we call sulfuric acid. It normally does that without taking part in the reaction. It just removes the water and it still remains sulfuric acid. So it doesn't necessarily become part of the reaction. Now let's see what happens. So we would have our arrow here, but we would show that our sulfuric acid is the dehydrating agent there. Okay? Now when that happens, we know that if we are dehydrating something, one of the products obviously is going to be water. So let me write it down as water there. Plus, what will be the other thing? Now if you check here, you would see that that part is what has been removed, is the H2O there. And likewise, because I know in the exam there we will also expect you to be writing showing these bonds here. Let me write the water molecule that has been formed, showing the bonds between the hydrogen and the oxygen molecule in that way. Now, what is remaining here, you would see is going to be CC. We have got now one of the hydrogen atoms here is gone, in fact, and the other one is from the OH group. But then we have got 1, 2, 3, 4 remaining. What is going to happen is that a double bond there is going to form, and the 4 hydrogen atoms, 2 will attach themselves to each of the carbon atoms available. Hence the formation of ethene when ethanol is dehydrated. So the dehydration of ethanol leads to the formation of ethene with water being formed there. Okay, now that is how the process of dehydration takes place. Of course, it could be other examples that we can look at if we had time. But quickly here, I want to talk to you about this type of reaction. Esterification. Now, this is the formation of an ester molecule, by the reaction of an alcohol and a carboxylic acid. Okay, now that is that is esterification. We are having the reaction between an alcohol and a carboxylic acid, and what is formed is an ester. Let's have a look at an example. Say we have this ester formed. Say we have methyl ethanoate. Now remember from the functional group lesson that we spoke about these terms here. If you see O-weight at the end, you know you're talking an ester. Okay? So this ester is methyl ethanoate. Now this ester, by virtue of being methyl ethanoate, that means it is formed from an alcohol of methanol, and the carboxylic acid was ethanoic acid. In other words, the O-weight part is the part of the acid, and the alkyl part is the part of the alcohol. So methyl will mean you had methanol reacting, with ethanoic acid. And then you formed this methyl ethanoate. How does that happen? Let's have a structural formula here. So methanol will simply be this one. You add this to ethanoic acid. Ethanoic acid will be, allow me to write the acid part this way. So you've got your H here, bonded to O, bonded to carbon atom, double to O, plus another carbon, and then you have that as your ethanoic acid. Now, the reaction will take place, and what is going to be formed when this reaction takes place, you would see here, this part here, you would have that part reacting together. And what is that? You're going to form the water molecule. Okay? There is your water molecule. Now, the two come together. The methyl group here, which is the CH3, joined together with that part of the acid molecule. So what you're going to have is this. You have that. There is the ethyl group. It joins there. There is the OC. Then you've got your double bond there. You've got your other C. You've got your hydrogen. You've got your hydrogen. You have your hydrogen there. And this thing, this part here is the ethyl group. You start naming that molecule from there. This will be ethyl. This part here is your O8 part. And how many carbon atoms are in it? 2. So this will be ethyl ethanoate. That's how an ester is formed. Ethyl ethanoate. Okay? Now, basically, you would say that the formation of an ester is a reaction between an alcohol plus a carboxylic acid plus a carboxylic acid, and that should give you the ester and water. That's generally the equation for esterification. Right. And lastly in this lesson, talking cracking. What is cracking? Cracking is the breaking down of organic molecules with huge molecular masses into organic molecules with smaller molecular masses. And this can be classified as a dehydrogenation reaction, because what you're doing, you are removing hydrogen all the time. You're cutting out huge molecules into smaller molecules. And this is exactly, although I don't have time to explain it here, this is exactly how Sasol and other companies like that in the world would produce the petroleums, the kind of organic molecules that we use every day, the petrol, the paraffin, diesel, all these things. The process of cracking helps them to actually get to the kind of molecule that we want, from huge organic molecules down to octanes, for example. Octane molecules have got 8 carbon atoms in their chains. So you coming from thousands of carbon atoms attached together to form chains down to those molecules with only 8. So we call that cracking. You're breaking these huge molecules down into smaller ones. And you, in the process, you produce some of the most valuable substances that we use in our everyday life. Now, that brings us to the end of this lesson for today. I hope you enjoyed it. And from me, Tinyiko Wamachabikosa, goodbye.